Déjame sangre. Bismillah ar-Rahman ar-Rahim. Okay, before we start our today's lecture, if you have any questions in the previous lecture or any other lecture, you can ask for questions, and then we will go ahead with the remaining slides of the lecture on the earthquake resistant design of reinforced concrete structures. Please, if you have any questions, you can ask questions.
Sir, what's the difference between seismic coefficient CA and CV?
Okay, what is your name?
Shasawar.
CA, if you look at the equations, the basic equations, you can see that the basic equation involves the factor CV, which is seismic coefficient taken from table 16R, RQBC 97. This is the basic seismic coefficient. And the subscript V indicates that this coefficient is dependent on the velocity of earthquake. Okay, and this is used in the main equation of the base shear. And in the other equation, for the maximum base shear, there is a factor CA, and CA is a factor, again a seismic coefficient, but this seismic coefficient is acceleration dependent. The subscript A indicates that CA is dependent on the acceleration of the earthquake waves. Okay, so CA is used in the maximum base shear equation. Similarly, CA is also used in the minimum base shear equation. Okay, this explanation is with regard to the seismic coefficient used in this equation. However, the derivation of these seismic coefficients, this is beyond the scope of this lecture. If you are interested in this derivation of this coefficient, you can go through the seismology books. You will find how the CA and CV are derived. However, with respect to the this response spectrum, I can briefly tell you that if you look at this flat part of the response spectrum curve, you can see a arrow in 2.5 CA here, which means that the maximum acceleration, you say this is the spectral acceleration on this part. So the spectral acceleration is equal to 2.5 times CA. Okay, 2.5 times CA, and CA is this thing. So CA is basically peak ground acceleration, if you are aware of this terminology from the seismology course. So CA is basically the peak ground acceleration, and 2.5 times of this is this thing, 2.5 CA. So 2.5 CA is in fact the acceleration, spectral acceleration, amplified acceleration or spectral acceleration. And this is the maximum acceleration that you can get on the response spectrum curve, because for the development of this response spectrum curve, as I said in the last lecture, most of the time the near field seismograms are used. So whenever near field records are used for development of response spectrum curve, now I think you will be able to understand that there will be an amplification between the short period structures and the short period seismic waves component which exist in the earthquake record obtained from the near field. So due to this amplification, you will get the highest values here in this low period values. These low period values, these are the period of the structures. So from low period, we mean to say that it's around 0.1 to 0.3 or 0.4 seconds. Within this region, you will get the maximum response. So the base shear value which you obtain from the base shear equation shall not be more than this, because it cannot be more than this. Any value on the response spectrum curve cannot be more than this 2.5 CA value. And the base shear equations which we have studied are designed such that any value which you obtain from the response spectrum shall be almost equal to the value that you obtain from the base shear equation. So whenever you use this base shear equation with the subscript CV on this branch of the curve, the value from this graph shall not be more than this value. So for this reason, the basic equation contains the value of the coefficient CV, and the maximum base shear equation contains the coefficient CA.
Thank you, sir.
Anything else? Any other question? Any other question from any student?
Excuse me, sir.
What is your name?
मोहम्मद जासिम सर. मेरा क्वेश्चन है लेकिन थोड़ा डिफरेंट है, इस लेक्चर से डिफरेंट है, लेकिन अर्थक्वेक एनालिसिस से रिलेटेड है, बिल्डिंग और अर्थक्वेक एनालिसिस.
चलो ठीक है, खैर आप कर लो क्वेश्चन.
सर लेट्स सपोज अगर हमारे पास दो वेव्स है ऑफ सेम फ्रीक्वेंसी बट डिफरेंट एम्पलीट्यूड.
क्या चीज दोबारा
सर
क्वेश्चन करें.
सर लेट्स सपोज वी हैव टू seismic waves of same frequency but different amplitude.
हाँ ठीक है.
Sir, now we know that if this frequency match with the frequency of the building, the resonance phenomena will occur. Now, how to know that whether the effect will be same or different due to these two waves?
Effect will be different. It is very obvious because you have in one record, you are having more amplitude. More amplitude means more energy. Okay, so with more energy, if there is a resonance, as I tried to explain in the last lecture, that if you have more energy in a acceleration in an earthquake record, so whenever resonance occur, more energy will be more damaging to the building, as compared to an earthquake record having less energy or less amplitude with the same frequency.
सर तो हम जब बिल्डिंग डिज़ाइन करते हैं ना सर, इसके लिए हम किस तरह पता चलता है कि मतलब एम्पलीट्यूड की बेस पे डिज़ाइन करते हैं या फ्रीक्वेंसी?
अच्छा, एक्चुअली जब हम बिल्डिंग डिज़ाइन करते हैं ना, तो हम बिल्डिंग डिज़ाइन के लिए जनरल बिल्डिंग्स के लिए उसमें हम टाइम हिस्ट्री एनालिसिस नहीं करते हैं. ठीक है, टाइम हिस्ट्री एनालिसिस हम नहीं करते हैं. उसके लिए हम स्टैटिक लेटरल लोड प्रोसीजर या रिस्पांस स्पेक्ट्रम यूज़ करते हैं. रिस्पांस स्पेक्ट्रम तो हर कोड में अपने अपने रिस्पांस स्पेक्ट्रम होते हैं, और इस पर कोड हमें वो रिस्पांस स्पेक्ट्रम इस्तेमाल करने होंगे. और स्टैटिक लेटरल लोड प्रोसीजर में हम बेस शेयर मालूम करते हैं, और उस बेस शेयर से जो वैल्यूज़ हमारे पास बेस शेयर की आ जाए वो उसको फोर्सेज में ट्रांसफॉर्म करके वो फोर्सेज, सेट ऑफ फोर्सेज हम स्ट्रक्चर के ऊपर लगाते हैं लेटरली, और उससे जो हमारे पास बेंडिंग मोमेंट्स आते हैं उन बेंडिंग मोमेंट्स को हम ग्रेविटी लोड बेंडिंग मोमेंट से जमा करते हैं, कंबाइन करते हैं, और उसके बाद फिर उसको हम डिज़ाइन करते हैं. हाँ, बहुत स्पेशल केसेस में जब हम टाइम हिस्ट्री एनालिसिस करते हैं, तो टाइम हिस्ट्री एनालिसिस के लिए हम एक रिकॉर्ड इस्तेमाल नहीं करते, बल्कि काफ़ी सारे रिकॉर्ड इस्तेमाल करते हैं. और वो डिपेंड करता है कि जहाँ पर आप स्ट्रक्चर डिज़ाइन कर रहे हो उस लोकेलिटी में प्रीवियस रिकॉर्ड ऑफ अर्थक्वेक क्या रहा है, और फ्यूचर में एंटिसिपेटेड अर्थक्वेक क्या हो सकते हैं. उसके बेस पे हम एम्पलीट्यूड और फ्रीक्वेंसी को सेट करते हैं. और या तो हम मोस्ट ऑफ द टाइम हम क्या करते हैं कि हम आर्टिफिशियल एक्सेलेरोग्राम जनरेट करते हैं, और बाज़ वक़्त हम देखते हैं कि दुनिया में अगर कोई अर्थक्वेक आया है और जहाँ पर मैं बिल्डिंग बना रहा हूँ अभी पाकिस्तान में या किसी और जगह, उसमें जो फ्यूचर अर्थक्वेक एक्सपेक्टेड है और ये पास्ट अर्थक्वेक जो कहीं दूसरी जगह पर रिकॉर्ड हुआ है, ये अगर मेरी ये पास्ट रिकॉर्ड जो किसी दुनिया के किसी भी जगह पर रिकॉर्ड हुआ है, ये मेरे उस रिक्वायरमेंट्स को पूरा करता है, तो मैं उन रिकॉर्ड को इस्तेमाल करता हूँ. और उसमें एम्पलीट्यूड और फ्रीक्वेंसीज में मतलब ऐसी होनी चाहिए कि जो मेरे लोकेलिटी के साथ मुताबिकत रखते हो. मसलन अगर मैं पेशावर में कोई बिल्डिंग बनाऊँ तो ज़ाहिर है कि ये एक मॉडरेट सेस्मिक जोन में आता है, तो इसमें एम्पलीट्यूड का मुझे पता होगा कि मॉडरेट सेस्मिक जोन में इतने एम्पलीट्यूड होंगे. अगर मैं जोन 3-4 में करूँगा तो मुझे उसके एम्पलीट्यूड्स हाई होंगे इससे. तो मैं जो रिकॉर्ड इस्तेमाल करूँगा मैं वो रिकॉर्ड इस्तेमाल करूँगा जो कि मेरे जो लोकेलिटी है जहाँ पर मैं बिल्डिंग कंस्ट्रक्ट करूँगा उसके साथ उसमें जो एंटिसिपेटेड अर्थक्वेक होगा फ्यूचर में उसके साथ उसकी फ्रीक्वेंसी और एम्पलीट्यूड मैच करूँ। ठीक है।
Okay, sir. Thank you, sir.
Any other question? If there are no questions, then we will proceed with this lecture. In today's first slide of today's lecture is very, very important from the earthquake load. You will get a bending moment diagram more or less of this shape. Okay, this bending moment diagram has been drawn on the tension side. You always draw on the compression side. It doesn't matter. However, the bending moment diagram look like this. You can see in the bending moment diagram for column. So you would have drawn bending moments. Can you see the screen?
सर स्लाइड
Yes, sir.
नहीं है सर।
Can you see the screen now?
यस सर।
Yes, sir.
Okay, so I was talking about the a frame subjected to gravity load, and you are familiar with the bending moment diagram being drawn for such a case. You can see this bending moment diagram for the gravity load.
Yes, sir.
So if you look at this bending moment diagram for a frame which has been subjected to gravity load in this form, a uniformly distributed load on the beam, okay, the bending moment diagram will look like this. You know this. So in this bending moment diagram, from this bending moment diagram, you can see that tensile stresses are produced in the bottom side of the beam at the midspan of the beam, correct? At the midspan of the beam, you have tensile stresses, and that's why you place your longitudinal reinforcement on the bottom side of the beam, okay, for this bending moment which occurs at the midspan. However, as you move towards the ends of the beam from the midspan, the direction of the bending moment diagram changes from negative to positive, okay, or from positive to negative, because you always draw a bending moment diagram like this, positive to negative. So we will say from positive to negative. And the at the ends, the bending moment direction changes, and therefore the tensile stresses which were previously produced on the bottom side of the beam would now shift to the top side of the beam here. So tensile stresses are produced on the upper side of the beam, at the ends of the beam, and they are produced on the bottom side of the beam at the midspan. You know this. On both, this is same for both ends of the beams. Tensile stresses in the upper part of the beam on both sides of the beams, ends of the beams, and tensile stresses on the bottom side of the beam at the midspan. Okay. Similarly, the column will have also tensile stresses in the exterior and interior part of the column as shown in this figure. You are very familiar with such kind of bending moment diagrams in the tensile stresses. And if a frame has been analyzed only for gravity load, what you will do is that you will place some reinforcement for this bending moment, which is you calculated from the analysis. You will calculate area of steel, and then calculate number of bars. And those number of bars will be placed on the bottom side of the beam for this mid-span positive bending moment. Similarly, for the negative bending moment, you will place reinforcement in the upper side of the beam here, and you can curtail some bars because the negative bending moment diagram does not extend to the full length of the beam. Similarly, you will also place bars on the exterior and interior side of the column. Usually, the equal number of bars are placed on all sides of the columns, as you have seen in several examples of the column design. So this is what you do for the gravity load. Now, if the same frame is subjected to gravity load, because whenever a building is being hit by an earthquake, gravity load would exist, and the building will hit this. The building would be hit by an earthquake. Okay, it is possible that that full live load does not exist at that instant of time, but the full load or superimposed dead load there when the building is being hit by an earthquake. So when this building is if the building is being hit at the base of the earthquake. So, okay, by calculating base shear and then force, we calculate this force and apply this force. When this force is applied at the story level, then the deformed shape of the frame will be like this. You can see the deformed shape. From this deformed shape, you can see that the tensile stresses will occur here in this part of the beam, and then tensile stresses will occur at the ends of the beam in the top side. On one side, tensile stresses will occur at the bottom side, and on the other side, the tensile stresses will occur on the upper side of the beam. Similarly, the exterior and interior tensile stresses will also occur in the columns. Now, this is when the frame moves from left to right. And because in the earthquake, the building will vibrate back and forth and back and forth. Therefore, the building is, but when this move from right to left, the direction of the tensile stress will change. Right, this will have the final bending moment diagram will be like this for beam, and this bending moment diagram will be for columns. Okay, and this will be bending moment diagram when the frame moves from right to left. So you can see from the bending moment diagrams that additional bending moments occur at the ends of the beam and at the ends of the column when the frame moves from left to right and right to left. How this frame shall be finally designed then? This frame must be designed for all the bending moments. For the bending moments which are coming from the gravity load and from the bending moments which are coming from the earthquake load in both directions. So now if we just look at one end of the beam, let's say the right end of the beam, here this one, the right end of the beam, the right end of the beam. So at the right end of the beam, you have a negative bending moment, which causes tensile stress in the upper fiber of the column, upper fibers of the beam. Okay, so normally we will provide some reinforcement for this, we know. However, now you have an additional bending moment diagram here, additional bending moment which is coming from the earthquake analysis. This bending moment must be added to this bending moment for the final calculation of area of steel and placement of reinforcement in the top fibers of the beam. So there will be more reinforcement in a frame analyzed for earthquake and gravity load both than a frame analyzed only for gravity load in the upper part of the beam. Okay, coming to the lower part of the beam. If you look at this lower part of the beam at the same location on the right, so there is no tensile stress coming from the gravity load, no tensile stress is coming from the gravity load. And normally we do not place any reinforcement in this part. By this I mean to say that if you place reinforcement for mid-span positive bending moment, you can curtail some of the bars as you move towards the ends in the bottom side of the beam. However, now in this case, in the case of earthquake analysis, you have an additional bending moment. This bending moment, if you look at this figure, so you have an additional bending moment on the bottom side of the beam. This bending moment must be, the structure must be designed for this bending moment. And this bending moment will give you some reinforcement, and that reinforcement shall be placed here on the bottom side of the beam, which was not the case in a frame analyzed only for gravity load. This is also possible sometimes. Sometimes in very high seismic zone, this is possible that you get a bending moment on the bottom side of the beam at the end of the beam, here at this location, where previously there was no reinforcement requirement. It is possible that in high seismic zones, you come across a bending moment which is higher than the bending moment at the midspan of the beam, and resulting in more reinforcement on the bottom side of the beam at the ends of the beam than the reinforcement placed at the midspan of the beam on the bottom side. This is quite possible in the high seismic zones. Okay, so and similarly, if you look at the columns, in the columns also you have additional bending moments coming from the earthquake analysis. This bending moment will be added to this bending moment. This will be added to this bending moments, and so on. So the conclusion is, what is the conclusion? Okay, one last point. The last point is that if you look at these bending moment diagrams and the tensile stresses, the resulting tensile stresses, they all occur at the ends of the columns and beams. They all occur at the ends and columns of the beam. They do not occur at the mid-span of the beam or mid-height of the column. You can see this in the bending moment diagram as well as in the resulting tensile stresses. This point is very important to be noted, that the earthquake forces will produce bending moments and tensile stresses only at the ends of the beams and columns. They do not produce any bending moment and resulting tensile stresses at the mid-span of the beam or mid-height of the beam. You can see from the bending moment diagram as well as from the tensile stresses. So finally, then we can conclude that earthquake loads or earthquake forces will produce additional bending moments at the ends of the beams, and where additional by additional bending moments, I want to say that in the top side of the beam, previously there existed some bending moment, but earthquake will give you more bending moments or additional bending moments at those locations on the top side of the beam. But on the lower side, at the bottom side of the beam, you didn't have any bending moment before the earthquake forces. Now, after the earthquake forces, you will have new bending moments. These are not additional, because previously there was no bending moment here at the ends of the beam on the bottom side. So you will have new bending moments on the bottom side of the beam at the ends of the beams, and additional bending moments on the top side of the beam at the ends of the beams. Correct? And at the mid-span, there will be no change in the bending moments for beams and at mid-height of the column. Okay. So the finally, what we will do is that we will place reinforcement at the ends of the beams and also on all sides of the columns. The mid-span reinforcement will probably not change at the mid-span of the beam, and because in the column we provide reinforcement from one end to another end, so whether there is a bending moment at the mid-height or not, it is of not very significance for us. Okay, so finally, the earthquake analysis will give us bending moments at the beam column joints, or at the ends of beams and columns. For this reason, we usually call that earthquake resistant design is nothing but the design of beam column joints and beam column joints. Okay, it's nothing but the design of beam column joints. Okay, if you have any question in this, you can ask your question. Otherwise, you will proceed, because this is a very important concept in earthquake engineering. that you get additional and new bending moments all at the joints of the beam column joints, and no bending moments at the midspan of the beam or mid height of the column. If you have any question, please ask your question, otherwise we will go ahead. Okay. So from this discussion, we conclude that additional reinforcement will be provided at the ends of the beams, both on top and bottom side of the beam. Okay, the reinforcement at the midspan of the beam will probably not change. And additional reinforcement will be provided for columns on all sides of the columns. Okay, so once this is done, okay, this was the design part. Then the ACI code requires that there are some provisions which must be fulfilled over and above the design. Okay, and these provisions are meant for safety of the structure. Okay, and these provisions are called as seismic provisions. Okay, and these seismic provisions are made to ensure adequate toughness under inelastic displacement reversals brought on by earthquake loading. And the provisions accomplish this goal by requiring the designer to provide for concrete confinement and inelastic rotation capacity. And no special requirements are placed on structures subjected to low or no seismic risk. Structural systems designed for high and moderate seismic risk are referred to as special intermediate respectively. Now, if you remember, while we were calculating base shear, we came across a factor called as R factor. And this R factor varies from 3.5 to 8.5. 8.5 is the highest value for R in the table. And with the increase in this value of R, the V base shear will decrease because R is in denominator. So if you use higher value of R, base shear will decrease. And a less base shear means less forces on the frame and less stresses in the frame, less bending moments in the frame, and economical design, because less reinforcement means economical design. But if you want to use high value of R, then there are code restrictions. The code would allow you to use high value of R, but then it places some restriction on the designer that those provisions of the code must be followed. And only then the designer can use the value of R equal to 8.5. Okay, so if the value of R is equal to 8.5 is used, the base shear will be less, forces will be less, the bending moments will be less, reinforcement will be less. This is one part. This is related to design. But then the code says that once you finish your design, then you must have to look at the especially at the connections of the beam column connections, and all beam column connections must have these seismic special provisions in place. If these seismic special provisions are not incorporated finally, then the R value that we have taken equal to 8.5 will not be correct, because this is a condition that when you take R is equal to 8.5, then the connections must be like this, which are explained in the next slides. These connections of the RC frame structures. So when we say the connections, you see the connections basically are the ends of the beams and ends of the columns. So the ends of the beams and ends of the columns must have some special requirements, which are illustrated in this lecture. In the remaining slides, you will see those. And this is done in order to make the structure more efficient in energy dissipating. And the energy dissipating capacity of the structure will increase, which means, in other words, that the structure will undergo several cycles of inelastic deformation without causing any threat to the life of occupants. Okay, and the damage will be controlled. So this can only be done if the connections have the details which are discussed in the next slides. So for this reason, the code has the ACI code, the current version of the ACI code has divided the frames into three types. The type 1 are those frames, structures, which are called as spatial moment resisting frame. And spatial moment resisting frame shall have special provisions, which we'll discuss in the next slides. And this is the most efficient type of frame. For this, R factor can be taken as 8.5, but then there are very strict provisions for this frame. And you will see that there are a lot of provisions which need to be fulfilled, and only then you can take R is equal to 8.5. This is spatial moment resisting frame. IMRF is another type of frame which is intermediate moment resisting frame. The intermediate moment resisting frame the R factor for intermediate moment resisting frame is equal to 5.5, less than the spatial moment resisting frame. So when R is equal to 5.5, you will have more base shear as compared to spatial moment resisting frame, and more force and more reinforcement. But then on the other hand, there is a relaxation in the provisions which are being placed by the code. You will see those provisions in the next slides. And there is another type of frame called as OMRF, ordinary moment resisting frame. In this OMRF, R factor is equal to 3.5, but then there are no provisions. There are no seismic provisions for this type of frame. Okay, this was with regard to the types of frames. Okay, now the ACI code further says that SMRF must be used in zone 3 and 4. No other frame structures can be used in zone 3 and 4. IMRF and OMRF are not allowed to be used in seismic zone 3 and 4. Only and only SMRF shall be used if somebody wants to use a frame structure in zone 3 and 4. So he must have to use a spatial moment resisting frame. And for this, all the provisions of spatial moment resisting frame shall be followed. IMRF is allowed to be used in moderate seismic zone, which are 2A and 2B. However, the code encourages the designer to use SMRF also in zone 2A and 2B. So, which means that SMRF can be used in moderate seismic zones, but IMRF cannot be used in high seismic zones. Similarly, OMRF is only allowed to be used in zone 1, and IMRF, SMRF are allowed to be used in zone 1 if somebody wants to use them in that zone. Okay. Then the code has categorized or has divided these provisions into two types. For SMRF and IMRF, these are different provisions. There are no provisions for OMRF. However, then there are some general provisions which are common to all types of frames. So in the coming slide, we will first of all study the common provisions to all frames, and then special provisions of SMRF, special provisions of intermediate type of provisions are seismic provision for intermediate moment resisting frame, no provisions for OMRF. Okay, so general provisions, general requirements for all types of frames are such that concrete to be used in the members of moment resisting frame. Okay, one more thing that I forgot to explain. When we say moment resisting frame, so by this you know that every frame can resist bending moments at certain locations, even if it is not designed for earthquake and if it is only designed for gravity. You have analyzed several frames subjected to gravity load, and you know that there is bending moment, positive bending moment at the midspan, negative bending moment at the ends of the beams, and whatever reinforcement is required, you place those reinforcing bars at the required location. So bending moments are there, and the structure, the frame resists the bending moments. But when we say that it is a moment resisting frame, by this we mean that it is seismic moment resisting frame. So though we do not write the word seismic moment, but it is basically seismic moment resisting frame. If a structure is designed only for gravity load and the additional bending moments which are coming from seismic action are not resist it, or the structure is not capable of resisting those additional bending moments coming from seismic event, then we cannot call that structure a seismic moment resisting frame. Okay, so by moment resisting frame, actually you mean seismic moment resisting frame. Otherwise, an ordinary moment resisting frame, which is not designed for seismic forces, which is not required for seismic forces, and analyzed and designed only for gravity load, will also resist bending moments, but these bending moments are coming from gravity load. If this structure is being hit by an earthquake, it will not have the capacity to resist bending moments due to the seismic event. So whenever we say a seismic moment, whenever we say moment resisting frame, by this we mean a frame which can resist seismic movements. And as I said earlier in the previous slide, that seismic movements occur at the beam column connections. So the beam column connections actually shall have the capacity to resist movements in an earthquake event. This is the conclusion, that the beam column joints, the beam column connections shall have the capacity to resist seismic movements coming from a seismic event. So only then you can call this as seismic moment resisting frame. And when we say that it is capable of moment resisting frame, then either it is very good in resisting the seismic movements. If it is very good, if it is very efficient in resisting seismic movements, it will be called as spatial moment resisting frame. And if it is not very efficient, less efficient than the spatial moment resisting frame, it will be called as intermediate moment resisting frame. And if it cannot at all resist the seismic movement, it will be called as ordinary moment resisting frame. Now, how a frame can be designed and constructed so that it has efficient connections. Efficient connections can only be produced if the provisions of ACI code are fulfilled, as you will see in the next slides, and I was trying to explain. So one of these provisions that the connections shall be efficient is this concrete strength. That concrete strength shall not be less than 3000 psi anywhere in the frame structure. Mid-span connection everywhere, the concrete shall have a strength, compressive strength coming from the cylinder test should be at least 3000 psi for all types of frames. Okay, there is no maximum limit on the ordinary concrete. If ordinary concrete is to be used, there is no maximum limit. 12,000, 10,000 psi, any strength can be used. Okay. However, in the case of lightweight concrete, some people would like to use lightweight concrete in order to reduce base shear, because you know that base shear is directly proportional to weight of the structure. So some people would like to use lightweight structures. If lightweight concrete is used in the frames, moment resisting frames, then the maximum strength allowed by the ACI code is 5,000 psi. It looks a bit awkward that why high strength is not allowed in lightweight concrete. The reason for this is that there is not enough data available to predict the anticipated behavior of the structure during an earthquake if lightweight high strength concrete is used in the structure. Then on the reinforcement, there are two requirements. In requirement number 1, if a designer wants to use a steel grade 60 conforming to ASTM A706, which is a low Li steel. ASTM A706 is a special steel which is much more ductile than the usual carbon steel or ASTM A615, and it has very good properties as compared to ASTM A615, and for this reason it is expensive also. If a designer wants to use ASTM A706 steel, how would you know that this steel ASTM A706 or not? The manufacturer of the steel will usually tell you that this is ASTM A706 steel, but then you can confirm by testing the steel in the lab whether it conforms to ASTM A706 or not. So if a designer is satisfied that the steel has all the properties of ASTM A706, he can use this steel, and there are no further requirements of the code if ASTM A706 grade 60 steel is used. In Pakistan, very few factories have started production of ASTM A706. Historically, only ASTM A615 has been used in Pakistan and also all around the world. ASTM A706 is only used in special projects like nuclear power plants, water retaining structures, and so on. But only very recently, only few factories have started the production of ASTM A706. Generally, the steel that you see in the market is ASTM A615. It is not ASTM A706. So if ASTM A615 is to be used, which is called as billet or carbon steel, then both grade 40 and grade 60 steel can be used, and they are allowed. Okay, they are available. Grade 40, 60, both are available in the market. But then the ACI code has placed 2 restrictions on ASTM A615, on the use of ASTM A615. The restriction, the requirement number 1 is that when you bring a steel sample to the lab, you test it in the lab, you get actual yield of the steel bar, then this actual steel bar minus the specified steel strength, yield strength. The specified steel strength for grade 40 is 40 KSI and for 60 is 60 KSI. So the difference between the two, actual yield is obtained from actual test minus the specified. This shall not be more than 18 KSI. For example, you bring a steel bar, steel sample to the lab, you test it, and you get a strength of, let's say, 80 KSI. Okay, actual yield that you obtain from the test in the lab. And the specified yield strength for this steel sample is 60. 80 minus 60 is 20. 20 is more than 18 KSI. So this steel cannot be used in the moment testing frame. Okay. The other provision is the ratio of actual ultimate to actual yield. You bring a sample to the lab to test it, to calculate the actual ultimate strength, the actual yield strength you calculate in the lab, and the ratio of the actual ultimate to actual yield shall be more than 1.25 or equal to this. If it is less than this, then it is not acceptable. An example to this will be, for example, you are using a grade 60 steel, and the actual ultimate from the test comes out to be, let's say, 90. Okay, and the actual yield comes out, actual yield, not the specified yield, comes out to be, let's say, 65. And the ratio of 90 to 65 is 1.38, so it is allowed to be used. However, if the actual yield comes out to be, let's say, 80, then the ratio of 90 to 80 is 1.125. So on the face, it seems good to have more yield and more ultimate, but the code would not allow you to use this. And the reason is that I hope you know that ductility starts after yielding. And the definition of the ductility, the strain ductility definition is that the strain ductility is basically the ratio of strain at ultimate to the strain at yield. So the larger the gap between these two parameters, strain at ultimate and strain at yield, you will get the larger ratios. And the smaller the gap between the two parameters, the less value you will get from this ratio. So the higher value means more ductility, the less value means less ductility, and you know that we would like to have more ductile steel used in our structures. So for this, these are two provisions of the ACI code, and these must be fulfilled. If a steel sample does not fulfill this criteria, it shall not be used in the moment testing frame. Okay. Next, the types of stirrups and ties, stirrups, cross ties, and hoops. As I said earlier, that the connections would be taking seismic movements. So these connections shall be properly confined, properly designed. Okay, and this confinement can be obtained by using stirrups in the beams and ties in the columns. There are several types of these confinement elements. If it is of this shape, it is called as stirrup. This is called basically an open stirrup. This is an open stirrup because the shape is like a stirrup. Okay. This is an open stirrup with two ends, both of them bent at an angle of 135 degree. However, if this stirrup open stirrup is closed with a cross tie single bar with one end 90 degree bend and the other end 135 degree bend, if it is placed on top of this stirrup, this will be called as stirrup plus cross tie, but also can be called as hoop or close tie. Similarly, this can be produced, hoop can be produced even from a single bar, starting from this 135 degree end and then complete cycle and finally ending at the same location where it started. So this will be called as continuous tie or continuous stirrup or closed stirrup. Okay, both of these are also called as hoop. The closed stirrup is also called as cross tie and stirrup. These are used in the beams and columns in order to confine the connection of beam and columns. Why these hoops ties and cross ties are used? They have several advantages. They carry the horizontal shear forces induced by earthquakes and thereby resist diagonal shear cracks. They hold together the vertical bar and prevent them from excessively bending outwards. In technical terms, this bending phenomena is called buckling. But this buckling is different from the buckling of the long columns that we have studied in some courses. This buckling is basically the buckling of steel bar, not the buckling of the whole column. The buckling of the whole column has nothing to do with this provision of the ties around the columns reinforcement. Okay, this buckling occurs in the steel bars when concrete in a column cracks extensively during an earthquake, and the steel bars, the bond between steel bar and concrete is completely broken at several locations. Then there is a possibility that due to the axial gravity load, steel bar buckles, which will further damage the column and can lead to the collapse of the column. So in order to avoid this at this final stage, to avoid the buckling of reinforcing bars at the critical final stage, the ties are provided very closely spaced. Ties are provided to prevent buckling of steel bars at this final stage, and to avoid collapse of the column at this stage. Okay, then they also contain concrete in the column. By containing concrete in the column means that when ties are very closely spaced, they will confine concrete as well. And when you push concrete in compression, then concrete tries to bulge out. This bulging out of concrete is also prevented, thereby increasing the compressive strength of concrete. I hope you know that confinement can increase the compressive strength of concrete manifold. From 3000 psi concrete, if you confine this, you can have a strength of, you can get a strength of 5000, 6000 psi or even more than that, depending on how the confinement has been provided. The confinement can increase the concrete compressive strength. Okay, this will also help in increase the concrete compressive strength. Okay, now from the next slide, number 65 onwards, there will be special provisions for special moment testing frame. First of all, we will study the provisions of the ACI code for beams and then for columns. Okay, in these slides are in the ACI code provisions. The ACI code does not use the word column and beam. The ACI code says flexure member, provisions for flexure members. However, uh, by flexure member, most of the time we mean beams, and from the compression members, most of the time we mean columns. So provisions for flexure members mean provision for beams. These will be discussed first. Okay, and the sequence of this provision is such that first of all the size restriction on the size of the beam will be discussed, then the reinforcement, longitudinal and transverse reinforcement, and so on. Okay, uh, these provisions, special moment testing provisions for beams, are only for those beams which are part of the special moment testing frame. Okay, all those beams, all those flexure members which are part of a special moment testing frame, and you have used in your analysis R factor of 8.5 during your analysis, these provisions must be fulfilled, uh, and only then the structure can be called as special moment testing frame, and it will be efficient in energy dissipation. Now we will take a break of 10 to 15 minutes, 15 minutes break, and then we will continue with the provisions for flexure member beams first and for columns, special moment testing frame. Once the special moment testing frame is finished, then we will quickly go through the INRF provisions. Okay, thank you. Okay, so we will start now the discussion on provisions for flexural members. These provisions applies to flexural members with factored axial compressive force less than or equal to AGFC prime divided by 10. It means that if there is a member with an axial compressive load which is obtained from analysis, such that it is less than the axial load carrying capacity of the column. You know that when cross-sectional area AG is multiplied with the compressive strength of concrete used in the member, it will give us the axial load capacity of that member. And divided by 10 means that 10% of this axial load capacity. Let's say from analysis we obtained 50 kip axial force on a member, and the axial load carrying capacity is, let's say, 100. So 100 divided by 10 is 10. Since the axial compressive force is more than 10, so this provision will not apply. Okay. However, if the compressive force is very, very small, as is usually the case in beams, then these provisions will apply to those members. So for this reason, most of these provisions most of the time will apply to beams. However, if there is a column in a very low-rise structure, and then the column is subjected to very small loads, like a frame structure supporting a GI sheet system, roof with trusses, lightweight trusses, and GI roofing. So the galvanized iron roofing system with the trusses will have very little load, and these loads, when transferred to columns, will be generally less than the 10% axial load capacity of the column. So in those very special cases, these are very special cases in which a column will be called as a flexural member, and these provisions will be applicable to the columns. However, generally speaking, in 99% cases, these provisions are applicable to beams. Okay. If a beam is part of spatial movement restricting frame, then the size of the beam shall be such that, number one, clear span to effective depth ratio of at least 4, which means that if length of the beam is, let's say, 15 feet from column to column, and the effective depth of the beam is 16 inch, then L by D, 15 into 12 divided by 16, 15 and 12, to convert this 15 into inches, is equal to 11.25. 11.25 is greater than 4. Therefore, this size of the beam is okay. However, if the length of the beam is, let's say, 5 feet, then for 5 feet, 5 multiplied by 12 divided by 16 is 3.75. 3.75 is less than 4. So this is not okay, which means that for very short span beams, the depth of the beam shall be kept such that the L to D ratio is more than 4. This provision has been kept by the ACI code for the reason that ACI code wants to make sure that the beam does not fail in shear, but it fail in flexure. You know that failure of a beam in flexure is a desirable phenomenon, unlike failure of the beam in shear phenomena, because shear failure is very abrupt and brittle, and therefore we would not like our beams to fail in shear. For this reason, if the beam is too deep and too short, then it is very highly likely that the beam will fail in shear, and the ACI code with this provision wants to make sure that the beam does not fail in shear. So for very short span beam, we would like to have a small depth of the beam in order to fulfill this provision of the code. Okay. Next is width to depth ratio. The width to depth ratio shall be more than or equal to 0.3. For example, if the width of the beam is 12 inch and the depth is 18 inch, so 12 divided by 18 is 0.67. 0.67 is greater than 0.3. Okay. However, if the width of the beam is 12 inch and the depth is let's say 60 inch, then 12 divided by 60 is 0.2, and 0.2 is less than 0.3, so this is not acceptable. From this provision, the ACI code wants to make sure that some kind of slender behavior which will result from a narrow and deep beam. Narrow while when the width is small and depth is more, so this may create slenderness of the beam along the depth of the beam, not along the length of the beam. This may cause some slenderness of the beam along the depth of the beam. So in order to make sure that this slenderness along the depth of the beam does not occur, the ACI code has placed this restriction. The other restriction is on the width of the beam, that the beam shall not be having width less than 10 inches. So the minimum width of the beam shall be at least 10 inches or more than this. Then this was on the size. These were the provision for size. Next are the provision for reinforcement. The minimum reinforcement, as you already know from your background, that minimum reinforcement in beams is these equations at all sections, critical sections. Maximum reinforcement has been fixed at 2.5% for all grade of steel, and 2 bars must run along the length of the beam everywhere. 2 bars, top and bottom, every location. Okay, these are the general requirement. Okay, then some specific requirement for certain locations. In the beginning, when we were comparing the frames subjected to gravity load with the frame subjected to earthquake load, so we finally concluded that when a frame is subjected to lateral load, the bending moments will be produced, additional bending moment will be produced at the ends of the beam on the top side of the beam, and new bending moments will be produced on the bottom side of the beam at the ends of the beams. Okay, in the frame subjected only to gravity load, the bending moment at the ends of the beam on the bottom side of the beam, they do not exist. So these are new bending moments which only exist in a beam which is part of a moment testing frame, and the frame is subjected to seismic actions. So for this reason, this is quite possible that sometimes you may obtain bending moments even larger than the bending moments at the midspan on the bottom side of the beam. In order to make sure that some minimum reinforcement exists on the bottom side of the beam at the end of the beam, the ACI code has placed this restriction. ACI code says that on the bottom side of the positive reinforcement at the end of the beam shall be such that it is at least 50% of the top reinforcement. So for example, if you have 8 bars as negative reinforcement, which you have obtained from the analysis and finally then design, okay, 8 bars as top bars, and from your analysis and design you obtained 3 bars. Finally, you calculate that 3 bars shall be used as bottom bars at the end of the beam. This you cannot do because of this restriction. You must have to increase the number of bars to 4 from 3, to make sure that this provision is fulfilled, because the provision is that half of the steel, which is used as top reinforcement, must be used. 50% of it must be used as bottom bars at the end of the beam. So when there are 8 bars here, at least 4 bars must be used. Whatever you get from design, if from the design you get 5 bars, it is okay. More than this is okay. 6 bars are also okay. But less than 4 bars are not okay because of these provisions. Okay. So, and this is true for both ends of the beam. This AS means area of steel, L means left side, negative means negative reinforcement. So area of steel on the left side, negative reinforcement, area of steel left side on the positive reinforcement shall be greater than or equal to 50% of this. Similarly, it is ASR, AS on the right side. So this AS steel on the positive side at the end of the beam must be at least 50% of this ASR. Okay. Next provision is that everywhere at all sections, this was only at the ends of the beams, anywhere in the beam, top, bottom, anywhere, mid-span, ends, everywhere, the minimum number of bars or minimum reinforcement shall be at least 25% of the maximum reinforcement at the joint. So the maximum reinforcement will be at the top side of the beam, at the ends of the beam, which is negative reinforcement. So this negative reinforcement will be the maximum reinforcement usually in the beam. Everywhere in the beam at any location, top, bottom, mid-span, end, the reinforcement shall be 25% of this. So in the previous example, where I was telling you that if there are 8 bars here, so at least 4 bars will be used here. Now 8 bars, if there are 8 bars here, 8 divided by 4, 25% means 8 divided by 4. 8 divided by 4 is 2. 2 bars will be used everywhere. However, if these bars are 12 bars, if these negative bars are 12 bars, then 12 divided by 4, 3 bars. 3 bars must be used top, bottom, mid-span, and everywhere, both for negative and positive reinforcement. This is another requirement of the ACI code for a beam, which is part of special interesting frame. Okay, next is the provision for ends of the beam up to certain length, and these provisions are with regard to transverse reinforcement or stirrups. Okay, the ACI code says that on both ends of the beam, from the face of the column up to a distance equal to twice the thickness of the beam. This face is face of the column, and from this up to a distance equal to 2h. For example, the beam is 2 feet deep, so 2 multiplied by 2 is 4 feet. In this 4 feet length from the face of the column on both sides of the beam, the stirrup shall be placed according to this requirement. Whatever the stirrup spacing is coming from the design, they shall be checked with this spacing. If that spacing is more than this, it is fine. But if that spacing is less than this, then this spacing criteria must be fulfilled. And it says that the spacing shall be at least d by 4. For example, in a 24-inch deep beam, it will be, let's say, 21 divided by 4. So it will be 5.5 inch almost. And then 8 into smallest longitudinal bar diameter. So whatever longitudinal bars have been used in the beams, the smallest longitudinal bar diameter. Let's say the beam, in the beam, the longitudinal bar diameter is 6 by 8. So 6 divided by 8, 8 will be cancelled with 8, it will cover 6 inches. Hoop bar diameter, which means the stirrup bar diameter. So let's say the stirrup bar diameter is 3 by 8, so it will be 3 by 8, 8 multiplied by 8, 24 divided by 8 will give us 3, and 3 multiplied by 3, 9 inch and 12 inch. So 12 inch, 9 inch, 8 inch, and 5 point something. This 5.5 inch is the least reinforcement, least spacing. So we will use this least spacing of stirrup in this region only, regardless of what has been obtained from the design. Okay, if from the design spacing is less than this, then it is okay. If from the design spacing is more than this, we will use this spacing of the stirrup in this region of 2h equal to 5 point, equal to the spacing, the least spacing obtained from these 4 equations. Then elsewhere you can use spacing of at least d by 2 at elsewhere. out of these regions. Lapping. Lapping of longitudinal bar will be very frequently required in the beam, especially on the positive side of the beam, bottom side of the beam. So on the bottom side of the beam, if lapping is required, lapping shall be avoided in the region of 2H from the face of the column and also in the midspan. Because midspan will have positive bending moment, maximum positive bending moment, and within the 2H region, we can have also positive bending moment, which is coming from the seismic analysis. So a lapping of the bottom bars will be avoided in the bottom of the beam, in the midspan of the beam, and at the ends of the beam in the 2H region. Okay, and then it is being shown by this yellow color. And this is only for the bottom bars. In the bottom, in the top bars of the beam, the lapping is to be avoided at the ends of the beam, but lapping is allowed in the midspan of the beam because negative bending moment is 0 here in the midspan of the beam. So lapping of top bar is allowed at the midspan. However, lapping of the bottom bar is not allowed at the midspan because from the gravity load bending moment will be maximum at the midspan of the beam. So lapping shall be provided somewhere between the midspan and this 2H region. This becomes very challenging in practical cases, but can be managed. Okay, and then the lap length. The lap length shall be equal to 50 diameter of the bar for FC prime equal to 3 KSI and Fy is equal to 40 KSI, and 70 bar for H is equal to 3 KSI and Fy is equal to 60 KSI. For example, if you have number 8 bar whose diameter is 1 inch, and FC prime is equal to 3 and this Fy, so this length shall be at least 70 inches, almost 6 feet. This should be 6 feet. Okay, instead of lap splicing, mechanical splicing is also allowed. I hope you remember on the lecture in our CD1 on splicing. Just like lap splicing, mechanical splicing is also allowed in the region where lap splicing is allowed. But there is an additional requirement of the code on the mechanical splice that whatever arrangement of mechanical splice is used for mechanical splicing, then the arrangement of the mechanical splice shall have a strength equal to 125% of the yield strength of the bar. By this, the code wants to make sure that no failure of the mechanical splice occur before yielding of the steel. The same provision is for welding. Welding of the steel is also allowed in the regions where lap splicing and mechanical splicing is allowed. However, a welded splice shall have a strength of at least 125% of the yield strength of the bar. So next are the provisions for columns. Provision for frame member subject to bending and axial load. So these are columns. If a column is part of spatial moment testing frame, then it should have these sizes and reinforcement. The size of the column which is part of spatial moment testing frame shall be at least 12 inches. And short, if it is a rectangular column, then short to long side ratio must be greater than 0.4, which means that 12 by 12, 12 by 18, 12 by 24 columns are okay, but 12 by 36 columns are not okay because then the ratio is less than 0.4. This is to avoid slenderness of column or to avoid the weakness of column in strength along one of the axes. Okay. The reinforcement shall range from 1 to 6% if a column is part of spatial moment testing frame, 1 to 6%. However, practically I have seen that very seldom will you be able to place reinforcement more than even 3%, because there will be a lot of condition of reinforcing bars inside the columns if the reinforcement ratio is more than 3%. So in our usual designs, we provide reinforcement not more than 3% because especially at the lap location, the reinforcement will be doubled, and there will be not enough space for concrete to flow around each and every bar and to make a perfect bond between steel and concrete. Okay, then on the ends of the column or beam column connection within the column. Within the column, you have seen that within the beam there were restrictions for transverse reinforcement. In the same manner, within the column up to a length of L0, but L0 has been defined. L0 has been defined by this larger of H1 RH2 clear span divided by 6 or 18 inch. Okay, larger of H1 or H2 means, well, let's say the column is 20 by 30. So the larger of this is 30. So this L0 shall be either 30 inch or clear span divided by 6. Clear span means clear height. Let's say the clear height is 10 divided by 6, or 18 inch. The least is 18 inch. So the L0 shall be equal to this, okay, and whatever L0 is obtained from this, the highest value of that shall be used in this for the value of L0. Let's say the value of L0 comes out to be 2 feet. So within this 2 feet distance from the bottom of the beam, the stirrup shall be provided, the ties shall be provided according to this criteria. The criteria is the criteria for the tie spacing is smaller of H1 or H2. As I said earlier, let's say H1 is 20 and H2 is 30. So the smaller of H1 is 20 multiplied by 2.25 or 20 divided by 4. So this is 5 inches. 6 into longitudinal bar diameter. 6 into longitudinal bar diameter means, let's say, if the bar is 1 inch, so this will be 6 inch, or S0. S0 will be explained on the next slide. Very seldom will you need this S0. Usually you will need 0.25 and 6 times longitudinal bar diameter. So whatever the least spacing comes from these three equations, that least spacing shall be used as spacing of ties within this N0 region. Okay. Elsewhere, the spacing can be used according to 6 into longer bar diameter or 6 inch. Cannot be more than 6 inch in any case, because it is the maximum spacing allowed in a column if it is part of facial testing frame. Okay, then wherever lap is provided, you will see in the next slide that lapping is only allowed in the center of at the mid height of the column. But wherever the lapping is provided, the lapping shall have in the lap region. In the lap region, the spacing of ties shall be at least D by 4 or 4 inches. Okay. This is the explanation of S0. S0, the basic equation for S0 is this. S0 is equal to 4 plus 14 minus hx divided by 3. This shall be less than 6 inch and more than or equal to 4 inches, 4 to 6 inch. So S0 will vary from 4 to 6 inch. And hx, what is hx? Hx is the maximum distance from one tie bar to another tie bar, or from one longitudinal to another longitudinal bar. Okay. And hx shall be less than or equal to 14 inch. The maximum value of h is 14 inch. These red color shows longitudinal reinforcement. This yellow shows continuous tie. This continuous tie is being placed, and then you have cross ties. One cross tie is this one along the long direction, and these two cross ties are along the short direction. Okay, so I will try to explain this through one example. Let's say hx, this distance. Let's say the total column is such that hx comes out to be 10 inch. So 14, let's say it is 11 inches. Okay. If hx is 11 inch, then 14 minus 11 is 3 inch. 3 divided by 3 is 1. and 4 plus 1 is 5 inch. So S naught will be taken as 5 inch, and this S naught shall be compared with this already obtained two values of S, and the least shall be accepted. Okay. If Hx is 14 inch, then 14 minus 14 will be 0, and this will be 4 inch. So with the increase in Hx, this S naught will decrease, because with the increase in Hx means that you have engaged less number of bars with the cross tie. So this Hx will increase with that. And then for that purpose, the vertical spacing between the ties shall be decreased in order to provide more confinement. Okay. This is with regard to the lapping. Lapping is allowed in the mid height of the column only, not at the ends of the column. At the ends of the column, lapping is prohibited, because you have seen that in the analysis of gravity load as well as of the lateral load, bending moment at the mid height of the column is mostly 0, and you have bending moments at the ends of the column. So this is the region where bending moment is 0, and in this 0 bending moment region, we can provide lap length. And when this lap length is provided, the length of the lap shall be equal to 50 diameter of the bar for 3 ksi, and F is equal to 40 ksi, and 70 bar this. And the spacing within the lap shall be equal to spacing of stirrups, spacing of ties shall be at least equal to by 4 or 4 inch. Connection, joints of special momentum frame. Okay, we have been using the word joints and columns very frequently. However, these two are different. Joint is a common location of the beam in column, which is denoted from this light blue color. Okay, this is the joint part. The connection part, however, extends into the beams and columns. This is one of the video. Let's see this video. You can see this is a test on the beam column joint. This was a research on evaluating the capacity of the joint in PhD research work. You can see clicking of the joint, moving of the joint. Okay. It's another video on an interior joint with when subjected to earthquake loading. You can see the movement of the frame back and forth. Okay, these joints of special frames are also they also require some special provisions according to the ACI code. So, successful seismic design of frames require that the structure be proportioned so that hinges occur at locations that least compromise strength. For this, weak beam, strong column approach is used. After design, the member capacities are calculated based on design section. A joint column flexure capacity will be greater than 1.2 times beam flexure capacity. Do you know that from the slide that we discussed in the beginning, that actions due to earthquake will occur around the beam column ends, at the beam column ends. So it will occur in the beam column joint, which is the common portion, and basically the joint part of the beam column connection is the part of column. Okay, because the load, axial load will be transferred through this joint. And then some part of the beam up to 2 inch on both sides of the beam, and L0 top and bottom of the column. This total portion is called as beam column connection, and the common part within the column is called as joint. So in order to, and you know that this inelastic deformations, cracking, and yielding of the steel will occur in this region, in both in beam and column. So the ACI code wants to make sure that if this inelastic deformations, cracking and yielding occurs, then the failure shall occur within the beam region, of the connection instead of the column part of the connection. Because if if the capacity of the column is less than, if the capacity of the column at the connection is less than the capacity of the beam at the connection, then spalling of concrete, cracking of concrete, and yielding of steel will disturb the load path, because the load is transferred from the floor to the column through the column. So if there is anything weak within this load path, then the structure can collapse. And when the load is passing through the column and column cannot withstand that load, so column will collapse and the whole structure will collapse. For this reason, the ACI code wants to make sure that during this inelastic deformation and cracking and yielding of the connection part, this activity is restricted or shall happen in the beam part instead of the column part, or it should happen in the beam part first and then in the column part. And so that if this inelastic deformation and cracking occurs in the beam part, only that particular story will be subjected to some kind of sag and deformation. The whole structure will not collapse. And hinges, the hinges will form at the beam ends, and then the action from a continuous frame will change into a hinge type of frame, and the occupants can have an escape time. They can evacuate the building once they see these things happening, and the structure will still be there. It will not collapse. For this reason, the ACI code wants to make sure that the beam connections are stronger. The connections, the connection part of the column are stronger than the beam part. So there are two requirements for this. One is that at the joint, the column flexural capacity in the column part shall be 20% greater than the beam flexure capacity. Okay, and the other is that column ties shall be continued to the joint. This we will explain on this figure. Okay, the figure on the left. The figure on the left is with regard to the MNB, means the nominal bending moment of the beam on the left side. MNBR means the nominal bending moment of the beam on the right side. This is for the positive bending moment, and this is a negative bending moment. And MNCT means positive bending moment, nominal bending moment of the column on the top side. This means nominal bending moment of the column on the bottom side. So when nominal bending moment of the column on the bottom, this one and this top, they are added together, their capacity shall be greater than the combined capacity of beam on the left and right, shall be greater than the column by 20%. Okay, 20% should be greater than this. And this is for the other direction. This was for the clockwise direction, and this was the anti-clockwise direction. The column, again, for the column, MNCL, MNC top, MNCB, and MNBL, MNBR means left, right, top, bottom. The summation of the column bending moments at the connection must be 20% greater than the beam combined bending moments. There is another requirement of the code for this joint part of the pitch moment testing frame, and it is that to prevent beam column joint cracking, ACI code requires that the column dimension, this column dimension parallel to the beam reinforcement, must be at least 20 times the diameter of the largest longitudinal bar. What does it mean? That this part is the joint part. This part is the joint part. I will make this red for you. This is the joint part. This joint part is part of the column. If you look at this, it's part of the column. So this joint should have a certain width, okay? And this, if this is the longitudinal bar in the beam, okay, then this joint, which is basically the size of the column, the size of the column, shall be at least 20 times this. Let's say this is 1 inch diameter of bar is 1 inch in the beam, then this dimension of the beam parallel to this bar shall be at least 20 inch. Regardless of what is coming from the size requirement of the code. So when in the beginning you assume the size of a column, let's say 18 inch, and finally you come to know that due to this 1 inch diameter of the bar that is being used in the beam, the column size shall be 20 inch. You will have to change this column size to 20 inch. This is also one of the challenging requirements from practical point of view. Another requirement at the terminal end are the exterior connection. At the exterior connection, there is a requirement that both top and bottom reinforcement in the beams must be carried to the far end of the column, as has been shown in this picture. The bottom and top reinforcement both has been carried to the far end of the column. And the development length with the hook shall be such that it fulfills the criteria of the ACI code, and this length shall be equal to FYDB divided by 65 FC prime, square root of C prime. So the development with the hook criteria shall also be fulfilled. If this criteria is not fulfilled, we will increase the size of the column. We will increase the size of the column in order to fulfill this criteria. These are provisions for special element string frame, and now we will, I think the remaining part of the lecture cover in the next week. Is enough for today. We have discussed the provisions for special element string frame. You should study these provisions, and if you have any question, you can come up with your question next time, and we will try to finish this lecture in the next week with the covering the remaining part of the lecture, and then one example. We will be trying to solve one example, and within that example, we will try to follow all these provisions of the ACI code. Okay, thank you. If you have any question, you can ask questions. Otherwise, today's lecture is over. Any question? Any question? You have any question? Any question? Anyone?
No, sir.
Okay. Okay, thank you. The next time we will try to complete this lecture. Thank you.